Hello everybody, welcome. This is paper 1 from May 2022 and this is time zone 1. I think this is a particularly challenging paper. It requires, I think in many places, a lot of interpretation and a lot of close reading. It's one of those papers where it's really important from the beginning to understand what a question is asking, and in this case a close reading is especially important. So I think this is actually quite a challenging paper. Let's have a look and see what we can do. Okay, first question is a 5-mark question. The front view of a doghouse is made up of a square with an isosceles triangle on top. The doghouse is 1.35 meters high and 0.9 meters wide and sits on a square base. The top of the rectangular surfaces of the roof of the doghouse are to be painted. Find the area to be painted. Okay, so 5-mark question, no subparts or anything like that. What are they asking us to do in this case? In the end, we want to find the area to be painted, but only of these rectangular surfaces on the top of the doghouse. So in this case, we're not asking for the whole doghouse or even this triangular part at the top. We're just asked to find the area of these rectangular faces here. This is the only part that is going to be painted. So not this, nothing else except for these rectangular surfaces at the top. This is the only part that is going to be painted, the top of these rectangular surfaces on the roof. Okay. So also a good idea, I think, when approaching a geometry problem is to mark up and sketch on the diagram as much as possible. The IB will rarely give information that is not essential or information that is like deliberately to trip you up. Not to say that it's impossible, but often the case that if information is presented, it's relevant and you can make use of it. Just the questions themselves, often they're presented in a very short way and condensed with a lot of information. So let's see what we can do here and sketch any information, any useful information on the diagram. Okay. So first off, they're telling us the front view of the doghouse is made up of a square, and then it has an isosceles triangle. So the front view is this portion here where we're looking at the doghouse, and they're telling us it's a square. And if it's a square, that means all of the dimensions of this doghouse are the same. So length, width, height, base, all of that is going to be the same. So that means that this right here is also equal to 0.9, of course, and more importantly, this height is also equal to 0.9 if the front view is a square. They're also telling us that there's an isosceles triangle on top. So an isosceles triangle, hopefully that'll recognize, not good enough, I'll just sketch it. An isosceles triangle, remember, has two side lengths that are equivalent, and then it also has two equal angles. For this question in particular, it's going to be important to recognize that we have, I guess, two equal side lengths for this isosceles triangle. So what does that mean? We know that these two are the same. And then the last piece of information that's actually pretty important for an isosceles triangle is, since we have two equal side lengths, that is to say, let me use this, let's say this and this are equal, and we have some symmetry, this angle and this angle are equal, we can divide our triangle, our isosceles triangle, exactly in half. And if we drop what's called an altitude, if we drop a line right from the highest point down to the base, it forms a right triangle. So we have two right triangles that are a mirror reflection of one another. So that's going to be important here as well. So if we drop this angle right here, or this perpendicular, I suppose, this line from the highest point to the base, we also have a right angle here. Okay, so there's a fair bit of information presented here. Another way to possibly work this out, just thinking about it, is if we know we just want to find this rectangular surface on top, we can say, okay, well, what would we need to find out this rectangular surface? Well, the area of any rectangle is just length times width. So we know that the length, given that this doghouse is on a square base, we know that this is 0.9 and this itself would be equal to 0.9. So we have the length. All we just need to find is I suppose, what we could say is the width of this rectangle, and then we would be good. And I think that's just about it. So this width itself corresponds to this W right here, and this W, this width right here, we don't yet know it, but we know it's part of a right angle triangle. And then some things should probably be kind of moving around, and you say, okay, well, it's part of a right angle triangle. That suggests either our trig functions or maybe even better, Pythagorean theorem. So we need to find this W, that's the missing piece, then we can multiply it by 0.9. How do we find this, and then how do we find this? Okay, so we know that the total height of this doghouse is 1.35, and they also told us that the front view of the doghouse is a square. So that means this is 0.9, this is 0.9, and this as well right here is equal to 0.9. So if we know if the total height is equal to 1.35, and we know, for example, that this height of the doghouse just up to this portion right here is 0.9, the question becomes, okay, well, how much further would we need to go if we wanted to reach our equivalent height of going right up to the tip? You know, base to tip is 1.35, this is 0.9, and so that this height, this h, must be the missing piece essentially. So what do we have? We have, and given a 5-mark question, we'd probably want to put this in. The height of this rectangular portion, or sorry, the triangular portion, is going to be the missing piece that we need to fill in. So 1.35 minus 0.9, and that would give us 0.45. And if we could call it h, I suppose we can. I'm going to move this to the side. It might be useful again, but I'll leave that for now. Okay, so there's our height right here, 0.45, and we can write that in. This is 0.45. So we have a right angle triangle. We know one side length. Let's go ahead and find this side length right here. And if we do, then we know we can apply our Pythagorean theorem, because we have two side lengths in a right angle triangle. This one isn't too bad. We know this whole base is 0.9. And so if it's 0.9 and we know our isosceles triangle divides this up into two equal sections, so here's one section, here's another section, we know that this itself must be 0.45 and this itself must also be 0.45, because 0.9 divided by 2 is 0.45. So 0.45. So this is also the base of this portion of our rectangular triangle. Okay, so we've got this rectangular triangle, this right angle triangle, and we know that this is 0.45 and this is 0.45. Now we want to find W. Pythagorean theorem is something that's not given in the formula booklet, but we know that for a right angle triangle we have a squared plus b squared equals c squared. So a, b, c, right angle triangle, we know that a squared plus b squared is equal to c squared. So the sum of the squares of the smaller side lengths equal the square of the larger side length of our triangle. So what do we know? We know that 0.45 squared plus 0.45 squared is equal to, in this case, w squared. So we can actually go ahead and solve that if you want. That would work. We can rearrange this as well and take the square root of both sides. And so if we do, we'll have w is equal to the square root of all of this business. 0.45 squared plus 0.45 squared. That should give us the width of this rectangular surface on the top of this doghouse. So 0.45, I'm going to work this out on the calculator that I have beside me. 0.45 squared, and then we want to take the square root of that. And that's going to give us a value of w of 0.6363 0.6396. So since we're not actually finished this question yet, I'm going to save a lot of digits. I'm not going to just keep 3 sig figs. I'm going to save a few extra. In the end, we're going to round it to 3 sig figs, so probably 4 or 5 should probably be okay. So there's W, the width. Last portion of this question, we know that the area itself, the area here, area of a rectangle is given by length times width. So let's go ahead and work that out. The length we know is equal to 0.9, and the width itself is equal to, and I'm going to save a lot of these digits, 636396. And again, working out on the calculator that I have beside me, I'm going to work this out. 0.9 times 0.636396. And this gives us a value of 0.5728. And of course that's just one of the faces. There's also one on the other side here. So we're going to multiply that by 2. So let's take 0.5728 and multiply it by 2. So 0.5728 times 2, and this should give us, so let's call this total area. This should give us a value of 1.15. And then if we wanted to, we could write meters squared. Okay, that looks good. Okay, so I think for this question, maybe some of the challenge comes in interpreting what it's asking and a close reading. So not only in terms of marking this up, but already from the beginning, recognizing that it's just this rectangular surface, not the whole doghouse, but just these rectangular surfaces. Then asking, okay, well, what do we need to find it? We already have this base right here, or this length, but we don't have this W, or the width, the slant height essentially. But we do have the total height, we do have 0.9, which again, we need to find, given that this is a square. And then lastly, if this is 1.35, this is 0.9, we have to travel a little distance more, 0.45. That corresponds to this. Again, we have an isosceles triangle, isosceles dropping in altitude, some line from the highest point down to the base, divides it exactly 2. So we know that this height is 0.5. This 0.9 is divided into 2. It's a right angle triangle. We find W, and then we've got our area. So yeah, fair bit going on. Sometimes with a 5-mark question without scaffolding, it's extra challenging because there's so many different paths. But there it is. Okay. 4-mark question. Let's have a look. A vertical pole stands on horizontal ground. The bottom of the pole is taken as the origin O of a coordinate system in which the top F of the pole has coordinates 0, 0, 5.8. All units are in meters. The pole is held in place by ropes attached at F, so F is the tip of this pole. One of the ropes is attached to the ground at point A with coordinates 3.2, 4.5, and 0. The rope forms a straight line from A to F, so from A to F right here. Okay, so what's going on here is we've got a 3-dimensional grid where this corresponds to X, this corresponds to Y, and then this is our height. So here we're saying we're 5.8 meters above the ground. This is kind of a rare question. Don't often deal with 3 dimensions, but we do, of course, it's on the syllabus. So let's draw a diagram and see what is going on. Actually, we'll draw a diagram a little later. Let's look through this first question. Part A asks us to find the length of the rope connecting A to F. So we want to find this length right here from A to F. 2-mark question. This question actually isn't too bad. we're given 3 dimensions, which makes it a little more challenging, but if we look to the formula booklet, we actually do have a formula for this. So let's go ahead and look at the geometry section of the formula booklet. So here we are, geometry and trigonometry, and distance between 2 points. Distance between 2 points when we have 3 dimensions, when we have x, y, and z. Okay, so here it is. Distance between x1 and x2, square that. y1, y2, square that. And then z1, z2, square that. So for this question, let's make sure to label each of the coordinates, and then we'll just use this formula. Okay. So here is our distance formula. I'll write it in. Distance is equal to the square root of, we have x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1. Not a bad idea to actually label these coordinates. It doesn't matter what we choose to be x1, y1, z1. As long as we're consistent, it should be okay. Let's choose this just because we'll avoid some negatives, at least in part. We'll get to avoid more negatives. x1, y1, z1, and let's call this x2, y2, and z2. Okay, so here's our distance once again. I want to take the square root of all of this business, and we'll have, oops, I guess I didn't avoid negatives in the end. But since we're squaring all these values, the negatives will go away. And we have 0 minus 4.5 squared plus, and now here we have 5.8 minus 0 squared. Okay, and that should give us our distance. So let's go into the calculator screen and work this out. So let's take the square root of, and the 0 minus 3.2, I'm going to write this out just exactly as it is, but essentially if we're squaring, we don't need the 0, and even this negative, since we take a negative and then we square it, it just turns into a positive. This would be equivalent to 3.2 squared, but let's write it out exactly as it is. Plus z2, this would be 5.8 minus 0. And we want to square that value. Okay, 0 minus 3.2, 0 minus 4.5, and 5.8 minus 0 squared. Okay, in this case we have 8.008. Let's write this out. Going back to the document here, distance itself would be equal to 8.008 or 8.01, and this is again in meters. All right. Part B asks us to find FAO, so angle FAO, the angle the rope makes with the ground. So FAO, remember we start at F, go to A, and then go to O. All right, so this is a 2-mark question. How can we solve this? There's somewhat tricky. I mean, we might say, okay, this is a right angle, and it really is. But since we're dealing with 3 dimensions, I'm actually going to draw a quick coordinate grid. And I hope this isn't, make it more confusing. But our 3-dimensional coordinate grid, if this is our z, so our height, we also have an x dimension, or we can call this y. Then we have this dimension right here. So we're dealing with 3 dimensions on this question essentially. And this would be y. So our xy grid that we normally have is now laid flat, and we have this z dimension kind of just going right through it, right through the center. And we have this rope. Here's the tip of our flagpole, and it's going down to some point A. So if this is F, for example, and this is A, we've got this flagpole, and the flagpole itself would be around this point right here, so along this edge. And the question is, if we wanted to, let's say, imagine that this is a right angle triangle. And we might say, okay, well, just a right angle triangle question. Let's use sine, cos, tan. We know that this is 8.01. And then we have another side length. And you might be wondering, okay, is it 3.2? Is it 4.5? I guess the danger would be to say that this is 5.8, which it is. And then the question would be, okay, can we use 3.2 or can we use 4.5? But it's really neither of these. For this question, what do we know for certain? We know the length from F to A is equal to 8.01. This is equal to 8.01. And we also know the height of this flagpole on 3 dimensions is 5.8. So we know that this right here is equal to 5.8. And now in that case, if we want to find FAO, so this angle right here, FAO, now we can use our right angle trigonometry. So let's go ahead and do that. I'm going to grab this, bring it over here, I'll leave it here, it's fine. So what do we have? If we want to find this angle right here, we have the opposite and we have the hypotenuse. So remembering SOHCAHTOA, we have the opposite and the hypotenuse. So we should use sine theta. Okay. So I'll try to fit it in here if I can. Sine theta is equal to opposite over hypotenuse. And in this case, sine theta is equal to opposite is 5.8 and the hypotenuse is 8.01. After that, you can go ahead and end solve. And I apologize for the lack of space or how condensed it is. But we can write this as also theta is sine inverse 5.8 over 8.01. Either of those should work. You can either end solve this original equation, or we can take the inverse, whichever you're comfortable with. Just make sure you are in degrees, of course. So 5.8 divided by 8.01, and this is going to give us a value of 46.39 or 46.4 degrees. Okay, so once again, distance formula for 3 dimensions is given to us in the formula booklet, and then given that we have a right angle triangle, we know this absolutely, and we know one other side, and that's because we know that our pole is centered at this point 0, 0, 0, and it just goes up 5.8. So we know this length, we know this length, and then we can write a right angle triangle and then use our SOHCAHTOA or our trig functions to solve. Okay. 2 somewhat challenging questions to begin with, I think. This one is, I think, not too bad. All right, 5-mark question. The height of a baseball after it is hit by a bat is modeled by the function height as a function of time, or h of t, is equal to negative 4.8 t squared plus 21t plus 1.2, where h of t is the height in meters above the ground and t is the time in seconds after the ball was hit. Write down the height of the ball above the ground at the instant it is hit by the bat. So for part A, we have this function which is an input-output kind of function. We input some value of t and it tells us the height of the ball at that given time. So we've got some function that tracks the height of this ball for any given time. And the first question is, write down the height of the ball above the ground the instant that it's hit. The instant that it is hit would correspond to t is equal to 0. So let's just substitute that in, and we can write this out more formally, I guess. Let's input a value of 0, and we have negative 4.8 t squared plus 21, t itself is just equal to 0. 0 squared plus 21 times 0 plus 1.2. For 1-mark question, we can also just know that if we input 0, all of these t values, anything with a t, since it's multiplied by 0, would go away, and we'd be left with 1.2. So that would be fine for a simple one more question. All right, part B, find the value of t when the ball hits the ground. Find the value of t when the ball hits the ground. So the time which the ball hits the ground. There are two ways to solve this. So if we think of just a conceptual idea of what is going on here, we have height as a function of time. The ball at t is 0 is 1.2 meters above the air, and it's a baseball, so it's going to fly through the air, and then it's going to hit the ground somewhere. And where is it going to hit the ground? It's going to hit the ground when h itself is equal to 0. So for our function, if we know here that h is equal to 0, that's our output, we could put an output of 0 and then ask the question, what are the t values that are going to make that true? 1.2. Now, you could potentially n-solve this. That is a possibility. But n-solve, remember, will find the value that is closest to 0. So if we were to stretch this back, for example, that would correspond to, and I'd imagine n-solve would do this. In this case, it would give you a value of like negative, I don't know, 0.6 t or something like that, which wouldn't make sense. In this case, we're looking for the point after the ball is hit. What is this point? T equals what? And for this question, I think it's probably going to be the easiest to graph it, so let's go ahead and do that. So here we go in the calculator screen. Let's go into the graph. Let's graph this function, negative 4.8 x squared, 4.8x squared plus 21x plus 1.2. All right. It's 21x plus 1.2. Okay. Graph is a little funny. We could probably change our x-axis, and we might want to. So for the next question, I'm just going to change the y value and maybe put the max to something like 50 should probably be okay. Oops, no. Okay. So let's find out where we reach 0 here. Analyze graph, and let's find the 0. Here we go. So after 4.43 seconds, the ball is at a height of 0. So let's go ahead and work that out. Or go back to the document then. Okay, so we know at this point right here we have 4.43 and 0, and so t itself, t is equal to 0. For a 2-mark question, either of these methods would work. You could set the height equal to 0 and then, oops, sorry, I don't know where that came from, and the value of t is equal to 4.43, or you could draw a sketch and then label the coordinate point where the ball has a height of 0 and label the time for that. So 2 method marks, substitute 0, find the value of t, or sketch and then show the coordinate point. Part C, state an appropriate domain for t in this model. Okay. So an appropriate domain, what are they talking about for an appropriate domain? So remember, domain are the set of inputs and the range are the set of outputs. In this case, our inputs are t. In this case, an appropriate set of values for t that we could feed into this model and expect a reasonable result. So given that we have a real-world context, we want to find a range of values of time that will produce a corresponding height of this ball within a certain domain. So what we want is we want t to be greater than or equal to something, or less than or equal to something. So for what values of t can we input to get a reasonable output? We know negative values of t wouldn't make sense. This is before the ball is hit. We know the ball is hit exactly when t is equal to 0, and t is equal to 0 would be acceptable. So we don't need to just have it greater than 0, but t is greater than or equal to 0 would also be okay. And then we know the ball hits the ground at 4.43 seconds, and so anything beyond that wouldn't produce a meaningful result. If we were to substitute into our function, the ball would be somewhere negative in the ground. So the last meaningful value for our domain, our set of inputs of t that's going to produce a reasonable result, would be 4.43. And remember, a domain for t, they're expecting this kind of inequality. So t is greater than 0, greater than or equal to 0, less than or equal to 4.43. All right. So just be mindful about the inequalities. They're expecting a range, a set of values, essentially. All right. 7-mark question. Let's see what we have here. 3 towns A, B, and C are represented as coordinates on a map where the x and y axes represent the distances east and north of an origin, respectively, measured in kilometers. Town A is located at -6,1, and town B is located at 8,6. A road runs along the perpendicular bisector of AB. This information is shown in the following diagram. Part A asks us to find the equation of the line that the road follows. Okay, so we know the road follows a perpendicular bisector of AB. This is this road right here, and we want to find an equation of this line. Okay, so how could we do that? They kind of scaffold us a little. They say, okay, it's a perpendicular bisector of AB. So essentially, just decontextualize, they're asking us to find the perpendicular bisector of AB. I think we can work through that from there. Okay, so what do we need to know if we want to find an equation of a line? And in this case, if we have a perpendicular bisector, if we find a point on the line and then a slope on the line, then we should be able to find the equation of a line. So where is this point on the line? How can we find a point on the line first? A point on the line itself would be the midpoint between A and B. So if we find that midpoint, we should be able to find a point on the line. And then, of course, how do we find the slope of this line? Well, this line, since it's perpendicular, is going to be perpendicular to the value of A and B. So let's work that out and see what we can do. Okay, so let's first find the slope of AB. And then if we know the slope of AB, we can find a line that's perpendicular to that. So slope formula is given to you in your formula booklet. It's y2 minus y1 over x2 minus x1, or change in y over change in x. So in this case, let's call this x1 and y1, and we can call this x2 and y2. Okay, so y2 minus y1, this is going to be 6 minus 1, y2 minus y1 over x2 minus 6 x1. Okay, I think that's good. 6 minus 1, 8 minus 6. Okay, I'm going to put this in the calculator just because there are some negatives here, and it's not a bad idea to see how this looks, I suppose. All right, 6 minus 1, and then we'll have 8 minus, and let's open some brackets, minus 6, and then we have 1/2, 7 over 14. Okay, so going back to the document here, we have 1/2, and we know that m AB, the slope of this line AB, is equal to 1/2. Okay, if the slope AB is equal to 1/2, and we know this road, which is a perpendicular bisector, is perpendicular to this, let's find the slope of M. So essentially we know M is equal to 1/2 the slope of this AB. Let's find M perp. Okay. Find M perp, or the perpendicular, switch the top and the bottom, and then multiply by a negative. So we have 2/1 multiplied by a negative, and this would just simplify to -2. Okay. So let's continue on. An equation of a line is in the form of y is equal to mx plus b. We know that m is equal to -2 in this case. And now the question is, what is b? And if we have a point on the line, we have a value of x and y, and that would allow us to solve for b. So right now we have x, y, and b. We have 3 unknowns, but if we can find an x and y value, then we'll have just 2 unknowns, and we could substitute and solve for that final unknown. So what is a point that's on the line? We said kind of earlier that it was this midpoint right here, or this halfway value. So let's find the point on this line, this value. Let's find this midpoint right here. Let's just call it midpoint. Okay. The midpoint itself is also given to us in the formula booklet. Midpoint formula is equal to x1 plus x2, or the average of the x values, x1 plus x2 over 2, and then y1 plus y2 over 2, or the average of the y values. So just substituting in again, we have -6 plus 8 over 2, and then our y values are going to be -1 plus 6 over 2. So just making sure this is both okay, -6 and 8, and -1 and 6. Okay. Working it out here, we'll have 2 over 2, and we will have 5 over 2. And in the end, this is going to simplify to 1, and we could write this as 5 over 2 or 2.5. I'm going to keep it, actually I'll write it as I'll keep it as a fraction, I suppose. 1 and 5 over 2. Okay, so we have an x and y value on the line. Let's substitute it into our equation right here, and then we can solve. So y is equal to 5 over 2. The slope we already knew was 2. X is equal to 1, and then b is what we need to find. In this case, we just have one unknown, so let's go ahead and solve for b. Let's go back to the calculator and work this out. So let's go menu, algebra, numerical solve, and we have 5 over 2 is equal to -2 times 1, or just essentially -2, plus b, and ask the calculator to solve for b. And b itself is equal to 4.5. So let's go back to the document. B is equal to 4.5. So find the equation of a line that the road follows. Let's use what we have here and write this out. Y is equal to -2x plus 4.5. So we found b was equal to 4.5 and our slope of -2. Okay. Town C is due north of town A, and the road passes through town C. Find the y-coordinate of town C. So here's town C, and it has some xy values, so we can even call it x3 and y3. We want to find the y-coordinate of town C. So what can we do? We know that town C is due north of town A. And so what does that mean? Due north means directly above north. So we just head not east or west in any kind of way, but just directly north. So here we are at town A, and we go directly north, and then we reach, let's see, town C. And so what does that mean? If we were on a coordinate grid, our x value, since we're not moving left or right, this x value of -6 would be the same x value that town C would have. So remember, it's written on some coordinate grid where x and y represent distances east and north. Since this is exactly due north, it is still -6 kilometers, I suppose, east of some central point. It's directly north. We don't go east or west, just directly north. And then we want to find its y coordinate. And so if we know it has an x value of -6, and we know it's on this line right here, we should be able to substitute into the equation and solve. So this is b right here. We have y is equal to -2x plus 4.5, and we know it has an x coordinate of -6. So y is equal to -2, and this is equal to -6 plus 4.5. And we can put that into the calculator. This would be 12 plus 4.5, or 16.5, and that would be the y coordinate. So due north means exactly straight north. So our x value doesn't change. We just head right up north. Don't go east or west. And if we know that the x value is -6, and we have an equation which relates x and y values, we could put in -6 and solve. All right. Here we go. Question number 5. The ticket prices for a concert are shown in the following table. And we have tickets for an adult are 15, child are 10, and student is 12. A total of 600 tickets were sold. The total amount of money from the ticket sales was $7,816, and there were twice as many adult tickets sold as child tickets. Let the number of adult tickets sold be x, the number of child tickets sold be y, and the number of student tickets sold be z. Write down 3 equations that express the information given above. This is kind of an interesting question, I think. So what do we have? I'm actually going to use a few different colors. Let's say x, and then y, and then this is z. So they told us that x is the adult tickets, y is the number of child tickets, and the z is the number of student tickets. So we want to write down 3 equations, and they give us 3 pieces of information here. We have x plus y plus z. So what's one equation we know? We know that all the tickets we sold add up to 600. So we know that adult, maybe I shouldn't have chosen 3 colors, but here we go. Adult plus child plus the student tickets, all of this will equal to 600. So remember, this is x corresponds to the number of, in this case, child tickets sold, adult tickets sold, student tickets sold, and so on. So x plus y plus z, this equals 600. That's how many tickets we sold. The total amount of money from ticket sales was $7,816. So what do we know? We know that for every adult ticket we sell, we make $15. So we have $15 for every adult ticket. Remember, x represents the number of adult tickets that we sell. So $15 for every adult ticket, plus we get $10 for every child ticket, and then we also have $12 for every student ticket. And altogether, that should equal $7,816. So x, remember, is our foundation, kind of our variable that we're working with. It's the number of tickets of each type that we're selling. All right, last part, let's try to use this equation right here. There were twice as many adult tickets sold as child tickets. Twice as many adult tickets sold as child tickets. So for these kind of questions, it's hard to know which one goes on each side. So let's write adult ticket equals, and then child ticket. But we don't know, but it isn't the case that the number of adult tickets is equal to the number of child tickets. There were twice as many adult tickets sold as child tickets. So x is the number of adult tickets. It doesn't equal the number of child tickets. we have more adult tickets sold. Number of adult tickets equals twice the number of child tickets. So there were twice as many adult tickets as child tickets. So if we sell, let's say, 1 child ticket, then we would have 2 adult tickets sold. So if you want, you can even just put in some values of this. This is x and this is, let's say, y. And if we imagine working this equation, when we sell, let's say, for every 1 adult ticket, we would have 2 x's. Let's say for 5 adult tickets. So if y is equal to 5, then our adults would be equal to 10, and so on and so on. 10, this would be equal to 20. And so this equation right here seems to work. For every single child ticket sold, we have twice as many adult tickets. That's an equation which relates the number of adult and child tickets. Okay, write down 3 equations that express the information given above, and part B asks us to find the number of each type of ticket sold. Okay, so what do we have? We have these 3 equations right here. We have one which is x plus y plus z is equal to 600. The second equation, 15x plus 10y plus 12z is equal to 7,816. And then we have one more equation right here, which says that the adult tickets is equal to 2 times the number of child tickets. Okay. What can we do? 3 equations and 3 unknowns. For this, we could use linear solve. So if we have a bunch of equations, this case we can't graph it because we have x, y, and z, and our graph only works for x, y, 2 dimensions. So in this case, we're going to need to graph this. Or sorry, not graph it. We're going to need to use linsolve. So let's go menu, let's go algebra, and solve a system of linear equations. Here we have variables x, y, and what's going to make this kind of tricky is we're going to have 3 equations. And the calculator works it out for us already. It gives us x, y, and z. And now after that, we'll put our values in our equations. We know that x plus y plus z is equal to 600. We know that 15x plus 10y plus 12z is equal to 7,816. And the last one, we know that x is equal to 2y. Number of adult tickets is equal to 2 times number of child tickets. Let's go ahead and work this out. And this is a solution to this set. And just to kind of double check, I mean, first thing, there's no fractional values, which is good. So we're not selling fraction of a tickets. And what this means is, remember x, y, and z, this is the number of adult, child, and student tickets. So x plus y plus z equals 600. 15, so this is the set of values that satisfies all of these. And here we have number of adult is equal to 2 times the number of child tickets. So this is a set of values that satisfy all of these. Okay, so find the number of each type of ticket sold. Let's go back to the document. This is part B, and we know x is equal to 308, y is equal to 154, and z is equal to 138. So the calculator gave us this, right? This is x, this is y. That's what it normally gives us when we have 2 coordinate points. But when we have 3, they also include this value of z. And we can still work it out as x, y, and z, and so on. And remember, that's what these mean right here. Okay. Question 7. A model art painting is contained in a square frame. The painting has a shaded region bounded by a smooth curve and a horizontal line. Here it is. Modern art painting. When the painting is placed on a coordinate axis such that the bottom left corner of the painting has coordinate -1, 1, -1, -1, and the top right corner has the coordinates 2, 2, the curve can be modeled by y is equal to f of x, and the horizontal line can be modeled by the x-axis. Distances are measured in meters. Use the trapezoidal rule with the values given in the following table to approximate the area of the shaded region. Okay, so they don't give us a function itself, but they give us the corresponding values at different points. So they want us to use the trapezoidal rule with the values given. Okay. Alright, so trapezoid rule, remember, is a way to estimate the area under the curve. If we start at this point, -1, -1, and we go up all the way to 2, 2, then we know we've traveled a distance from -1 to 2. We've traveled a total distance of 3 in this case. From -1 all the way to +2. We've traveled a total distance of 3. And it looks like, in this case, for our trapezoids, we have a value of -1. We have a value of... Actually, let's put it on this axis right here. We have a value of 0, and we have a value a little further, so 0, 1, and 2. So if this is once again our y value, this -1, this would be the value of -1, 0 right here. And it might be helpful if we were to actually construct something like a coordinate grid for this, I think, potentially, and then stretch it across. So this is 0, 0, here, and here. So we know when x is equal to -1, we have a height of 0.6. And then when x is equal to 0, we have a height of 1.2. And when x is equal to 1, we have a height again of 1.2. And when x is equal to 2, we have a height of 0. Remember, all trapezoid rule does is it constructs a set of trapezoids here. And with only 3 trapezoids, we can almost actually just use the formula for a single trapezoid. But let's work this out and use the trapezoid rule itself. I think it should be okay. So there's a few other trapezoid rule questions already covered in some other videos. So trapezoid rule is given to you in your formula booklet. It's the area under a curve with some starting point and ending point of some function f of x, and then this x is always matched together, can be given by 1/2 h, and then we open up some brackets, and we have y0 plus yn, the starting y value plus the final y value, plus 2 times, and then we have y1 plus y2 plus all the way up to yn minus 1. And what that means is it's everything up to the second last one. Remember, this is the last one right here. So let's go ahead and write those values in. H in this case is one that we'll need to solve for, and h, remember, corresponds to the size of the intervals. Usually they'll tell us the range, that is to say the total value from beginning to end point that we want to sweep through, and they'll tell us the number of intervals. In this case, they just give us a set of values, and in some sense they ask us to infer it. So h is the size of the intervals. And so what is it? If we're going from -1 all the way to +2, and we do it in this case 3 steps, we have 1, 2, 3 equal intervals, and we know we travel a distance of 3. In this case, the size of the intervals are just going to be 1. So we know that h in this case is equal to 1. The height at the very beginning is equal to 0.6. The height at the end, right here, is equal to 0, plus 2. And then these points, remember, are shared by 2 different trapezoids. It's shared by this trapezoid right here, and it's also shared by this one right here to the right. So that's why we multiply the inner values by 2. 2 times, and then this inner value of 1.2, just right here as well, plus this other inner value of 1.2. And then we can close our brackets. Remember, when you're working through this, we're multiplying this whole thing right here by this value out in front. So be mindful of your brackets as you work this out. Okay, let's go to the calculator and find the value. Get a new screen. And so we have 1/2. Yeah, let's get a fraction, I suppose. 1/2 times 1. We don't really need to put that 1 there, so I'm going to skip it. And let's get double brackets. So we have 0.6 plus 0, again, not entirely necessary, plus 2 times 1.2 plus 1.2. Okay, so we want 1/2 to multiply all of this. I think, again, it's a good strategy to find out the value of what's on the inside on your calculator and then multiply 1/2. If you set it out like this, just make sure you have the double brackets. All right, and then we have the area of this section is equal to 2.7. Okay, so let's go back to the document and write this out. 2.7. Okay. Approximate the area of the shaded region. Okay, good. The artist used the equation y is equal to negative x cubed minus 3x squared plus 4x plus 12 all over 10 to draw the curve. Find the exact area of the shaded region in the painting. Okay, so the exact area of the shaded region in the painting. So remember, for the shaded region under a curve, we can use our integral. So this trapezoid rule right here gave us an estimate for the area under the curve. And that's why, actually I should probably write this out actually right here. This is an approximation. So the trapezoid rule gave us an estimate for the area under the curve, but the true area under the curve is given by this integral, given by this right here. So the sum of the values, or the area under the curve, with some starting point and ending point of some function f of x. And then we want to keep these x's, or the variables, always the same. And for AISL, it's always x. All right, so this is our function right here. This is our f of x. In this case, we should be able to just plug this in, and if we know our starting point and our ending point, we should be able to find the exact area of the shaded region. So let's go ahead and work that out. So our starting point is -1, that's our lower bound, and we're going to go all the way up to 2. That's going to be our upper bound. Our function itself is negative x cubed minus 3x squared plus 4x plus 12, and this is all over 10. And then we want to integrate this. Essentially what we're doing, we're taking the integral. We want to integrate this with respect to dx. And of course this should just match the variable that you have as the input. Okay, so that's it. Let's go to the calculator and work that out. Menu, calculus, we want to find the numerical integral. Our lower bound was -1, and our our upper bound was 2. Our function, actually let's get a fraction to write this out, and we have negative x cubed minus 3x squared plus 4x plus 12, and this is all over 10. Our variable is x, so let's write an x right in here. And there it is, 2.925. So let's go back to the document and write this out. 2.925. Find the exact area of the shaded region. Okay. Find the area of the unshaded region in the painting. Kind of an interesting question. I'm going to actually erase a lot of this here. Pretty much everything actually. And I think I'll leave some of this trapezoid rule just because it can stay, I suppose. Alright, so we know that the area of this shaded region, we just found it out, and the area of this shaded region was 2.95. So this is, let's call it A1, and it equals 2.95. And we want to find the area of the unshaded region, so everything that is, well, not within the shaded region, essentially. And so what is the area of this shaded region? Or sorry, the area of this total thing? What do we have? We know that it's a square frame, and we know the dimensions of the frame. We found that at the very beginning. If our x value starts at -1 and goes up to 2, we travel a distance of 3. Similarly, if we start at a y value of -1 and go up to 2, or just knowing that it's a square frame, we have again a value of 3. So the area of the frame itself, we can write it as area of the frame minus area, change this to s of shaded, minus as should give us the area of the unshaded, we can say. So the area of the frame is 3 by 3. The area shaded is 2.95. And then by definition, what is not shaded is unshaded. And so let's have 3 by 3, 9 minus 2.95. This gives us an area unshaded. And area unshaded is equal to 6.05. You could just write 6.05 here, and that would be fine as well. Okay, not too bad. All right, question number 7. Leo is investigating whether a 6-sided die is fair. He rolls the die 60 times and records the observed frequencies in the following table. So he gets a 1 8 times, a 2 7 times, a 3 6 times, and so on, so on, so on. Leo carries out a chi-squared goodness of fit test at a 5% significance level. Now we have a few questions in terms of our hypothesis test. So write down the null and alternative hypotheses. That's our part 1, or question A. So the null and alternative hypotheses. In this case, we're doing a chi-squared goodness of fit test. There are two types of chi-squared tests. One is an independence test, and the other is a goodness of fit. Goodness of fit asks whether a distribution maps on to what we would expect it to. So oftentimes they'll have questions where it says, Joni is seeing whether such and such a situation maps onto a normal distribution, where we have some kind of bell curve. In this case, they're wondering whether the die is fair. And that's the question, or the initial hypothesis that, in this case, Leo is trying to find out. So if we were to write out HO and H1, or the alternative and, sorry, the null and alternative hypothesis, the null is the die is fair. The die is fair. And the alternative would be that the die is not fair. Essentially, it's opposite. So what Leo is doing is he's rolling this die. He's not sure whether it's a fair die or not, whether it might be weighted. So he rolls it 60 times, and he has the observations from these 60 trials. And he wants to say, okay, well, does this distribution match what we might expect? And there are two options. Either the die is fair or the die is not fair. We could also write this out as probabilities. Probabilities are all equal. So in this case, we wouldn't have a normal distribution. We would have every single probability for each of these 6 die. Since it's a 6-sided die, we would expect the chance of getting a 1, 2, 3, 4, 5, 6 to be equal, all the same. So the null hypothesis, if the die is fair, the probabilities are all equal. If the die is not fair, then the probabilities are not all equal. So we could write probabilities are, and then we might say not all equal. And on the actual test, of course, write this out. Okay, write down the degrees of freedom. Degrees of freedom, you remember, is rows minus 1, columns minus 1. This is for chi-squared goodness of fit, or sorry, chi-squared independence, but it also works for chi-squared goodness of fit. Goodness of fit, we're only ever going to have either 2 columns or 2 rows, but for just ease of memory, I think have one formula that applies to all situations. So rows, we have 1, 2, 3, 4, 5, 6. 6 minus 1, and then of course columns. Rows, we actually only have 2 rows. 2 rows. So in this case, 2 minus 1, but columns we have 6. So this will be 6 minus 1. 1 times 5 is just going to give us 5 in this case. 2 minus 1 times 6 minus 1. Alright. Write down the expected frequency of rolling a 1. So expected frequency is how many times you would expect to get a 1. And this is not in terms of what is observed, but just taking the situation as itself. Expected, if we had a fair die and we were to roll it, let's say 60 times, how many times would we expect to get a 1? So for our formula, we have EX, this is in the formula booklet, is number of trials times probability of occurrence. And in this case, we have 60 trials. We roll the die 60 times, and the probability of us getting a 1 would be 1/6. If this is a fair die and every single side has an equal chance of showing up, we would expect the probability of being a 1 or getting a 1 to be 1/6. And so 60 times 1/6. 1/6 of the time we would expect to get a 1. We roll it 60 times. Altogether we would expect to get 10 1s. Alright. Next question, asking us to find the p-value for the test. So p-value, we're going to need to run a chi-squared goodness of fit test. So let's go to the calculator here and work this out. So chi-squared independence test is where we would construct a matrix. Chi-squared goodness of fit, since we only ever have 2 rows or 2 columns, eventually we're going to present this as columns, we just want to use our spreadsheets. So let's go ahead and, in this case, let's actually write observed and expected. Oops, I think I put 0. Let's write observed and expected. So this is what we observe. Number of 1s was 8, and we had 7 2s, 6 3s, 15 4s, and so on. 12 5s, 12 6s. It's just a coincidence that they match up here. Essentially what we want to do is we want to write the observed values and the expected values and see essentially what the difference is between. Is it something that varies too much? Does the difference between observed and expected vary too much? Alright, so our expected frequency. We found out the probability, the expected frequency of rolling a 1 was going to be 10. And the probability of rolling a 2 would be the exact same. So if we're rolling this die 60 times and the probability of getting any of the number is 1/6, we would expect, again, 10 2s, 10 3s, 10 4s. That is to say, if all of these have an equal chance and we roll it 60 times, we would expect these 60 trials to be divided up evenly between all of these values. Alright, so we've got our observed, we've got our expected. Let's go to menu, statistics. I want to do a stat test, and we want to do the chi-squared goodness of fit. Our observed we called O. Our expected we called E. Degrees of freedom we need to find. Sometimes they'll scaffold, sometimes they won't. And in this case, degrees of freedom is 5. Let's go ahead and find our results. And there it is. Our p-value is equal to 0.2872. So let's go back to the document and write this out. So our p-value is equal to 0.287. State the conclusion of the test, give a reason for your answer. So conclusion of the test, sometimes they'll say in context. In this case, they're just asking for a conclusion. So, and then give a reason, justify. So we have a 5% significance level, and we have a p-value of 0.287. So what we could say is 0.287 is greater than 0.05, or similarly, 28.7% is greater than 5%. Our significance level, our p-value, 28.7%, You can kind of think about that as the probability that our null hypothesis is true, or again, the probability that we kind of see these results just based on chance alone. And just based on chance alone, we see we're going to have these results roughly 28.7% of the time, which is, not terribly unlikely. Almost like a third of the time we're going to see this, and it's definitely not enough for us to say that we can reject the null hypothesis. So in this case, we're going to see these results 28.7% of the time. Null hypothesis is true. We're going to say the probability that it's true is 28.7%. In that case, it's enough for us to accept HO. And you could write accept HO. You could also say we fail to reject the null hypothesis. The mark scheme says that accept HO is, of course, it says condone HO, but technically this is actually the proper answer. We don't say conclusively that it is the case that the null hypothesis is fair, but we fail to reject. It's something of not as strong of a claim. Fail to reject HO. Otherwise, we accept it. All right. Or you could also as well, look at the mark scheme a little earlier. This is also acceptable. The die is fair. Die is fair. So this is your justification, and then this is the conclusion. All right. Question 8. A factory produces bags of sugar with a labeled weight of 500 grams. The weights of the bags are normally distributed with a mean of 500 grams and a standard deviation of 3 grams. So already we kind of know we're in the realm of normal distribution. Write down the percentage of the bags that weigh more than 500 grams. So 1 mark question here. So part A, sometimes it's a good idea to draw a sketch to kind of see what is going on here. So we have a situation, number of bags of sugar, they're normally distributed. We have a mean of 500, and we have a standard deviation of 3 grams. Write down the percentage of the bags that weigh more than 500 grams. And in this case, it's going to be all the values to the right of the mean. And since this is the line that divides it, without even using NormCdf, we can, of course, we know that this is equal to 50%. One of the things that is kind of tricky on this is they're asking for the percentage of bags. So looking at the mark scheme, if you were to write 0.5 or 1/2, it would actually be marked as incorrect. So just be careful. If writing down the percentage of bags, we would want to write out a value of 50%. Okay, let's go on to part B. I'm just going to move this because I think I might need the space. Part B. A bag that weighs less than 495 grams is rejected by the factory for being underweight. Find the probability that a randomly chosen bag is rejected for being underweight. So here we go once again. This is, in this case, a 2-mark question, so we'll be expected to show some process. I'm going to actually redraw this just to make it a little nicer, or thereabouts. Mean of 500, and we want to find a probability that a bag weighs less than 495. So let's draw a line. It's going to be to the left here, and it would be 495. And we want to find the probability that a bag weighs less than 495. All right. So we're looking for this area right here. In this case, we have the cutoff point, and we want to find the area. So this is going to be NormCdf. That is to say, we're looking for this percentage to the left of this cutoff point. So let's go ahead into the calculator. Let's go Menu, Probability, Distributions, and we're in NormCdf. Lower bound we can keep as this massively negative number. Usually, you just want to make sure that you sweep out all the area to the left. So usually like 5 standard deviations is enough. So you could put 100 and it should be fine, but this massive negative number should be okay as well. Upper bound, 495. This is our mean, and our standard deviation was 3. All right, so it looks like roughly 0.04779, or roughly 4.8% of the bags are underweight. So let's go and write that out. For a 2-mark question, this would actually be your process. You can also write NormCdf, and then we can write -999, 495 lower bound, and then this would be our mean, and this would be our standard deviation. 0.04779, and we want to find out the probability. We can represent this as a decimal or fraction or percent. So to 3 sig fig, 0.4, and then this 9 would go to 8, so we have 478 if you want. 4.78%, all the same. Okay, part C. A bag that weighs more than k grams is rejected by the factory for being overweight. The factory rejects 2% of bags for being overweight. Find the value of k. Okay, so this is a 3-mark question, a little more challenging here. Same idea. I think it's always a good idea to draw a graph, just because it helps scaffold things, so far as I see it at least. So a bag that weighs more than k grams is rejected for being overweight. The factory rejects 2% of the bags for being overweight. So in this case, if it's more than a certain cutoff point, so now we're looking for a cutoff point and not a percentage. We have the percentage. If it weighs more than k grams, it's rejected. And 2% are rejected. So in this case, we're looking for a point right here, or thereabouts. And we want to say, okay, well, if we know that 2% are rejected here, 2% of the bags are rejected here, what is this cutoff point k? And what makes this a challenging kind of 3-mark question is the idea that, remember, our calculator sweeps out from left to right. So if this is 2%, then we know that everything to the right here, or sorry, everything to the left, is going to be 98%. So when asking the calculator what areas should we sweep through, it's not 2%. If we chose 2%, it would actually just be this area right here, which would give you a very small number, or one that definitely wouldn't be overweight, not greater than the mean. So we're asking the calculator to sweep through 98%. So let's go ahead and go back to the calculator screen to work this out. Menu, probability. In this case, we want to go inverse normal. So the area that we're asking the calculator to sweep through is 0.98. The mean, remember this mu is the mean, and the mean was 500, and our standard deviation was 3. Alright, so there it is. A bag must be equal to 506.16 grams. If you were to work this out and you were to put 0.02, you'd get a value less than the mean, and then hopefully that should be a signal that this can't be overweight if it's less than the average. Alright, let's go back to the document and write this out. So this is what we did. We did inverse normal, and we fed in an area of 0.98 with a mean of 500 and a standard deviation of 3. And we got a result of 506.16, or just 506. So what do we know? We know that this k value is equal to 506. Okay. All right. Question number 9, 7-mark question. The function f is defined by f of x is equal to 2 over x plus 3x squared minus 3, where x cannot be equal to 0. Just an idea, why can't x be 0? Because we're dividing by x. And just as a little aside, because this is quite a common question, this would also be the point where we would have an asymptote, because we can't divide by this number at the bottom. This would be where x is equal to 0, would be our asymptote, this line that we approach, but never touch, right? That we never really reach. Okay. Let me erase this. Okay, so here's a function, and they ask us to find the derivative, f prime of x. Okay, not too bad of a question, pretty common question. A calculus question almost, not always, but straightforward derivatives, yeah, they're possible, but often we have this variable in the denominator, which we have to work with. Alright, so here is part A. F of x is equal to 2 over x plus 3x squared minus 3. And we know if we want to take the derivative, so I'll write it out here. This is given in your formula booklet. We have x to the power of n. If we want to take the derivative and find f prime, we multiply this exponent out in front, and then it's reduced by 1. But the question here, like, x is always just, well, just by itself. It's not, they never give us 1 over x. What do we do in these cases? We always want x to be just presented not where it's in a numerator. So we don't want it at the bottom of a fraction. We want to write x as with essentially whole number as just a plain value in some sense. We don't want it over in our denominator. So how can we change this 2 over x? So once again, I think we've done this before in some past videos as well, but 1 over x is equal to x to the negative 1. 1 over x squared is equal to x to the negative 2, and 1 over x to the n is of course equal to x to the negative n, whatever it is. So if we have, I'm just going to draw a little more space, if we have, let's say, 2 over x, we can represent this as 2 times 1 over x, and then this just becomes 2 times, and we know what this is just x to the negative 1, so this is 2x to the negative 1. So you can separate them, and I think that's not a bad idea. So 2 over x becomes 2 times x to the negative 1 plus 3x squared minus 3. And remember, this is still f of x. We haven't yet derived it, so don't yet put a prime here. Don't yet put a prime like that, because it's not quite the case. Here's f prime. Now we can derive it. So let's take this exponent, multiply it out in front. In this case, we have now negative 2x used to be negative 1. Let's take away 1 from this. So now it's negative 2 plus, again, grab this exponent, multiply out in front. 3 times 2 is 6. X used to be 2, take away 1, now it's just 1. And then any constant just goes away, so these plain numbers just go away. And that's our derivative, negative 2x to negative 2 plus 6x. Find the equation of the normal to the curve y equals f of x at 1, 2 in the form of ax plus by plus d is equal to 0. And then it says where a, b, and d are, and this z means whole numbers. So whenever they want us to present an equation of a line where everything is on one side and we just have a 0 on the other, they want us to write a, b, and d, any of these values, no fractions, no decimals or anything like that. Bring everything to one side, set the other side equal to 0, no fractions, no decimals allowed. These are called integer values. So integer values. Okay, so let's see what we can do. Okay, so we want to find the equation of the normal to the curve. So if we have f of x, I'm actually just going to graph this to kind of show you what it looks like real quick. So get a new window and then graph it. So here we are, 2 over x plus 3x to the negative 2 minus 3. So here's our function, and we want to find at this point negative 1, 2. So I'm just going to find this point when x is equal to 1, y is equal to 2. We want to find the normal to this curve. And so what that means is we want to find a line that's perpendicular. So not tangent, which is just going to be the slope at this given point. We want to find the perpendicular. So I'm going to go back to the document and actually sketch this out. And so as quickly as I can, I suppose, try to provide some more idea. So here's this sketch. We have this asymptote at 0 again. And then it goes down, something like this. And here's this point at 1, 2. At 1, 2. And we know if we wanted to, we could find the tangent to this line, right? The slope of a line at a given point. But in this case, we want to find what's called the normal. And that is to say, we want to find the line that is perpendicular to the tangent. So the normal to this function. Not the tangent, but this is the normal. Okay, and I suppose you can kind of see what is happening. If this is m, then the slope of this would be m perp, and that would help us find the equation of the normal to a given line. So, how can we work this out? We want to find this perpendicular to this function right here. Two parts of an equation of a line, a slope, and then the y-intercept. We have this set of points here. So we have a set of points on the line. We can find that y-intercept, but how can we find the slope? So we know that this derivative right here is given by negative 2x to the negative 2 plus 6x. And this is also called our slope function. So remember the gradient function, the slope function, the derivative, all of these things, they tell us the slope of a line at a given point. So that's what this f prime of x does. And if we have an x value here, if we know that x is equal to 1, we should be able to put that into our slope function and find the slope of a line at a given point. So let's go ahead and do that. So f prime of 1 equals negative 2, and let's input this value, and then we should be able to find the slope at that given point. So I'm just going to work this out on my calculator that I have beside me, and it's going to be negative 2 plus 6, of course, which is just going to be 4. Alright, so we know that the slope of this line at negative 1, 2 is equal to 4. So I'm actually going to write that in here. So this line right here, the slope of this tangent line at this point 1, 2 is equal to 4. Okay, so if we know that m is equal to 4, then m perpendicular, so 4 is the same as 4 over 1, m perpendicular is going to be equal to 1 over 4 multiplied by a negative. Okay, so now we've got some part of our equation of a line, y equals mx plus b. We know that this is negative 1 over 4x plus, and the question is, well, what is b? Okay, so we have a point already on the line. We have x and y values, so we actually have a point that's on this normal line. So we should be able to actually just substitute this value of 1 and 2 into the equation. So y is equal to 2 when x is equal to 1, and then we can find the value of b that way. Y is equal to 2, x is equal to 1. And we can, you can end solve for that if you want. It would be 2 plus 1 quarters, or it would be 9 over 4. If you do end solve this, and you do get a decimal, I think it's going to be easier if you write it out as a fraction, just because in the very, very final step, we want to write it out as this form right here, without any kind of decimals or fractions. And it's easier to convert fractions to whole numbers than decimals, I think. Okay, so our equation of a line in the end is y is equal to negative 1/4 x plus 9 over 4. And they want us in the end to write it out in this form. This ax plus by plus c is equal to 0. by plus d, thought it was. Alright, plus d is equal to 0, where this a, b, and d can have no fractions, no decimals, just whole numbers. Positive, negative whole numbers. Okay. So, first off, let's bring everything to one side. Let's bring this x over and this 9/4 over. Essentially what we're doing when we're bringing something to one side, we're doing the opposite. So we're adding 1/4 x to both sides, and then when they meet, negative 1/4 x, positive 1/4 x, they cancel out. But you can also think about it, when you bring it to the other side, it just has to change its side. So bringing this negative 1/4 x to the other side, it becomes positive 1/4 x. This y just stays here as it is, and bringing this negative 9/4 over to the other side, it's now going to be a negative 9/4, and that equals 0. Okay, so we have these fractions here which we don't really want. This over 4 equals over 4. This is 1/4 of an x. So if you imagine something like this, here is, let's say, a whole x, but we don't have a whole x at the moment, we just have 1/4 of an x, so this is like 1/4 of an x. But we want a whole x, we don't want any fractions or anything. What can we do is we can multiply it by 4, and that'll get rid of our fraction. This will apply in any case. If it's 1/5, just multiply by 5. And then for this 9/4, since it's also over 4, we don't want 9/4, we just want whole numbers. So we multiply everything by 4, multiply everything by the fraction. And so, let's multiply by 4, multiply by 4, and then of course this 9/4, we're going to multiply by 4 as well. So that'll just give us x, plus 4 times y gives us 4y, and 4 times negative 9/4 just gives us negative 9. There it is. X plus 4y minus 9 equals 0. Okay, there it is. Not a bad question. Okay, 6-mark question. Carl has 3 brown socks and 4 black socks in his drawer. He takes 2 socks at random from the drawer. Complete the tree diagram. So here we have first sock, second sock. He takes 2 socks at random from the drawer, and then just looking at this, here he has 7 total socks and 3 brown, and now he has 6 total socks and 2 brown. So if he selected a brown, we know there's 1 fewer socks and then also 1 fewer brown socks. Essentially what we have here is non-replacement. We're not putting the socks back. So if he selects a black sock right here, then after that, how many black socks does he have? Well, he only has 3, and he has 1 sock in his hand, so he only has a total of 6. Binary events as well. This should be 3, 6, and 3, 6. Remember, these need to add to 1. Okay. Find the probability that Carl takes 2 socks of the same color. So how does that happen? He can either have a brown sock and a brown sock. That will result in him having 2 socks of the same color, or he can take a black sock and a black sock. So to find the probability that he gets a brown, if we have a tree diagram here, we just multiply along the channels. In this case, we'll have 6/42, or if we simplify this a little more, how could we do this? 6/42 be 3/21, or 1/7. And then if we multiply along here, black times black, 4/7 times 3/6 is going to be 12/42. In this case, 6/21, or what could we say? 2/7. Okay, so 1/7 of the time he has 2 browns, 2/7 of the time he has 2 blacks. In both cases, he has a pair of socks that are the same color. So let's write that out. So what can we say? If we wanted to, this might be a little more than you need. P same is equal to, let's say, P black plus P brown. For a 2-mark question, you probably wouldn't want to, well, I mean you could, but might not want to put this level of detail into a question. 2/7 is equal to 3/7. Alright, so the probability that he has two socks of the same color is 3/7. Okay, and remember, probability questions, decimal fraction percent are all acceptable. Alright, part C. Given that Carl has two socks of the same color, find the probability that he has two brown socks. So given that, so we're in the realm of conditional probability, that he has two socks of the same color, find the probability that he has two brown socks. So in our formula booklet, we have a formula for conditional probability, and it looks like this. PA given B is equal to PA and B over PB. So conditional probability we often want to read from the back to the front, where we're dealing with some subset, and then we're saying out of that subset, what is the probability that we have, let's say, a smaller portion within that subset. So in this case, given that Carl has two socks of the same color, so in his hand he has two socks of the same color, like two socks of the same color, maybe it's double black, double brown. Given that he has two socks of the same color, find the probability that he has brown socks. So out of all the socks that are the same color, what fraction of those are brown? Essentially that's what we're asking. So let's go ahead and work this out. I think, to be honest, a lot of these questions with conditional probability are going to be easier to solve if we think about it conceptually. So let's write this out. So the probability that he has the same socks. 3/7 of the time he has socks of the same color. And out of that fraction, out of that portion where he has the same color, what fraction of those are brown socks? So here it is. 2/7 of the time he has black, 1/7 of the time he has brown. So 1/7 out of that 3/7 he has brown. And in this case we could write this as, you can put this into your calculator, in the end we'll get 1/3. And I guess I can try to represent this. Maybe I will. I'm going to try to show an example. So these are the total socks that he could have if he selects 2, and we know that he could get brown black, he could get black brown, and so. And what do we know? 3/7 of the time, this is maybe 3/7 of the time, this is him getting 2 of the same color. This is probability that he has the same color. But there are ways that this can work out. Let's see. Let's say this is maybe a little overkill, to be honest, but this is 1/7 of the time he has brown socks, and then black socks would just be within here, 2/7. Altogether he has 3/7. What fraction of that 3/7 is brown? Well, 1/7 of that 3/7 is brown. And so the answer is just 1/3. I think conceptually is the easiest way to work these out, rather than the formula. Okay, this is the question I suppose that I had alluded to earlier when I said that there were some questions on here that required a lot of interpretation. This is, I think, the most challenging question on the test. Let's have a look. The strength of earthquakes is measured on the Richter magnitude scale with values typically between 0 and 8, where 8 is the most severe. The Gutenberg-Richter equation gives the average number of earthquakes per year, n. So average number of earthquakes per year is n, which have a magnitude of at least m. So the magnitude, this is the strength, and it's measured in m, and then the number of earthquakes per year is given by n. Okay, for a particular region, the equation is log base 10n equals a minus m for some a, and we say a is a real number. Essentially, a real number is anything that you could put on the number line. So it could be like root 2 or root 5, it could be pi, it could be infinity, actually anything up to infinity, any value you want essentially. This region has an average of 100 earthquakes per year with a magnitude of at least 3. Find the value of A. So this is a logarithmic equation right here. It looks a little challenging, a little intimidating, but at the end of the day, it's an input-output question. We have n, which we don't know, a, and m, 3 things we don't know, but they give us 2 out of the 3 unknowns. So if we have 2 out of 3 unknowns, input those values and essentially n solve. Looks intimidating, but it's an input-output question. So a region has 100 earthquakes per year. 100 earthquakes per year is given by n. So we know n is equal to 100, and with a magnitude of at least 3, so which have a magnitude of at least m. So in this case, we know that m is equal to 3. So for finding the value of a, I'll just put part a here. This is our equation. Log base 10 of n is equal to a minus m. What do we know? We have log base 10 of n is equal to 100, a minus, and m is equal to 3. After that, input output, let's n solve for a. Okay, so let's go to the calculator screen and work that out. Menu, algebra, numerical solve. In this case, we're going to want to find our log function right here. Log base 10 of 100. So it kind of scaffolds us in terms of what values to put in. Then we have a minus 3, and then we want to solve for a. Okay, and the value is 5. So let's go back to the document and write this out. A is equal to 5. Okay. Question B. The equation for this region can also be written as n is equal to b over 10m. Find the value of b. Okay. So this is actually going to be important for later. This question kind of reads almost like a paper 2 in that you need to draw from earlier parts. So find the value of b. So this is still for this given region, this unidentified region, but we're still within that region. And we know that n is equal to 100 and m is equal to 3. So once again, n, m, and b, 3 things, 3 variables we don't know, but we do know n and m. We know 2 out of the 3. So again, we can actually n solve in this case. So let's write that equation out. N is equal to b over 10m, and n we said was equal to 100, b we don't know, and m was equal to 3. And in this case, once again, we can n solve for b. So let's go back to the calculator and work this out. Menu, algebra, numerical solve. 100 equals, set up a fraction, b over 10 to the power of 3, and then we ask calculator to solve for b. Alright, so it looks like 100,000. So b is equal to 100,000. Alright. Not too bad so far. Not too bad so far. Part C. Given that m is greater than 0 but less than 8, find the range of n. Okay. So given that m is greater than 0 and less than 8, find the range of m. Alright, so this one requires a fair bit of interpretation, I think, and some context to try to see what is going on. So m is the magnitude of an earthquake, and n is the number of earthquakes. So what do we have here? Given that the magnitude itself is greater than 0 and less than 8, find the range of n, the number of earthquakes per year. And this is where I said it kind of reads somewhat like a paper 2. In terms of finding n, we would have to go back to this equation right here. So n, remember, is the number of earthquakes. The number of earthquakes, we found out what b was. b, we said, was 100,000. And m is, in this case, the magnitude, which have a magnitude of at least n. m is the magnitude or strength of the earthquakes. So given that we have a strength that is greater than 0, but less than 8, find the range of n, the number of possible earthquakes. So how would we find n? Well, it's given by this equation right here. So let's go ahead and write that out. N is equal to, we found out what b was, over 10m. And so I suppose one thing that might kind of scaffold or cue this question is this is a rather peculiar question in itself, this one right here, finding the value of b, because they already asked us to do something with this skill, this input-output question, for part A, that they would ask us to essentially solve another input-output question in this context, unless they wanted us to do something with it potentially. So maybe that would be potentially a question to ask. How could we use this question? Are we going to need to make use of this value of A or B or so on? Okay. So number of earthquakes is given by 100,000 over 10 to the power of their magnitude. And in this case, we're looking for earthquakes which have a magnitude greater than 0 and less than m. So let's find the total range for n. So if m is, let's say, equal to 0, let's find the range of n. So m is greater than 0. We have 100,000 over 10 to the 0. You can put this in your calculator. Anything to the 0 actually is just 1. So we have 100,000 over 1. In this case, 100,000 earthquakes, which I suppose kind of makes sense in some sense. Like if they're infinitely small, we would expect potentially a lot of earthquakes. And so this would be the upper bound. So this would be the upper bound. This is like the highest number, the upper bound. And let's go ahead, and we also have, n is equal to 100,000. That was the value of b, over 10 to the m. But in this case, we also have 10 to the upper end of 8. And so what could this be? So once again, what we're doing here, we have this equation which gives us the number of earthquakes. Number of earthquakes is equal to 100,000 divided by 10 to the power of the strength of the earthquakes. So if we have strength of the earthquakes between 0 and 8, what are the total range of number of earthquakes that we could possibly have? So if we put in the lower bound of 0, that is to say super weak kind of earthquakes, we could have up to, let's say, 100,000 in this certain region. And if we put in a value of m for a very strong earthquake into this equation of n is equal to 100,000 over 10 to the m, if we put in a very strong earthquake, what are the total range of number of earthquakes that we can have? So 100,000 over 10 to the 8. I'm going to work that out. Actually, no, I'll go to the calculator to work that out. So on the calculator screen, set up a fraction, 100,000, 10 to the 8, and it gives us 1 over 1,000. Let's actually write this out as a decimal, 0.001. So let's go back to the document here. 0.001. Okay, so the total range, the range of n, in this case we want to use inequalities, and we would say that n is greater than 0.001, using the same symbols here. We're not including, so n is greater than 0.001 and less than 100,000. All right. Okay, so kind of a challenging question in terms of interpreting what it's asking. All right, let's go on to question D. Within this region, the most severe earthquake recorded had a magnitude of 7.2. So m was equal to 7.2 in this instance. Find the expected length of, oops, sorry, I think there's something actually right above. The expected length of time in years between earthquakes with a magnitude of at least m is 1 over n. Okay. The expected length of time in years between earthquakes with a magnitude of at least m is equal to 1 over n. Okay. Within this region, the most severe earthquake recorded had a magnitude of 7.2. Find the expected length of time between this earthquake and the next earthquake of at least this magnitude, giving your answer to the nearest degree. So we have this equation, and we're coming back to it. This is a pretty central equation, I suppose, right here. Going down here, looking at this one, same thing, except our b value, which we found, is here. The number of earthquakes is equal to 100,000 divided by 10 to the power of m. This will tell us the number of earthquakes that we could possibly expect of a given magnitude. So writing it out once again, 100,000 over 10 to the m. In this case, we have a magnitude of 7.2. So what this formula gives us is it's going to tell us how many 7.2 magnitude earthquakes would we expect within 1 year. So we have 100,000 divided by 10 to the, and then m was equal to 7.2. So super strong earthquake, how many would we expect to have a year? So let's go into the calculator and work that out. I'm going to set up a new screen. Let's get a fraction. 100,000 divided by 10 to the 7.2. In this case, very, very small number. N is equal to 0.000631. So going back to the document, N is equal to 0.000631. And this is actually 1, 2, 3 sig figs, so that's okay. All right. So how many of these massive earthquakes would we expect to have a year? Well, the number of earthquakes we would expect to have a year is a very, very fraction of a percent. It occurs very, very infrequently. So n, the number of earthquakes that we would expect to have of this magnitude every year, is we wouldn't even expect to have one of these earthquakes. The expected length of time in years between earthquakes with a given magnitude is equal to, of at least m, is equal to 1 over n. So we found out what n is equal to, and that means 1 over this value of 0.000631. In this case, if one of these earthquakes, we would expect to have how many earthquakes of this magnitude every year? Not even one. So if we take 1 over this value of 0.00631, that would tell us how long between earthquakes we would expect between, such violent, heavy magnitude earthquakes. So working this out, I'm just going to work it out on the small calculator that I have beside me. We have 1,584.78 0.79 rather, or 1,580 years, I guess, to 3 significant figures. Alright, let me just see if this is all correct. 10,000 divided by 0.00. Whoops, sorry, I think I forgot 1 0 here. There shouldn't be so many zeros here. This should only be 0.006. And in that case, in this case, this should be 0.00, and that would make this 158 years. Okay. 150. See. 5. Just 158. Let me just change this decimal point real quick. 479. Okay, so 158 years. I just want to type this in just once more. 100,000 divided by 10 to the 7.2. Okay. Good. Alright. So I think that's a pretty challenging question. In terms of just interpreting what it's asking and keeping track of n and m in this case. Alright, so I believe there's 2 more questions to go. Let's have a look. A company's profit per year was found to be changing at a rate of, so this is change in profit as a function of time, is equal to 3t squared minus 8t. So remember, this dp over dt gives us the change, the instantaneous rate of change. It's our slope function, remember the derivative. So the change in profit for a given unit of time, where p is the company's profit in thousands of dollars and t is the time since the company was founded, measured in years. Determine whether the profit is increasing or decreasing when t is equal to 2. So we have this formula right here, dp over dt. It's given by 3t squared minus 8t, and this gives us the slope of the line at any given point. So not knowing this function itself or what it might look like, at least to the beginning, if this is profit and time, and we might have, changes in profit and time, maybe there are good times and bad times and so. But if we want to find the slope of a line at a given point, which is what our derivative does, it would give us the change in profit as change in profit per time. And that would be something that would allow us to find out whether our profit was increasing or decreasing at a given time. So if we know change in profit as a function of time is given by this function right here, what is the case when t is equal to 2? So let's substitute. Let's say 3, input this value of 2 for t, and we know that at this point we have, I'm going to work this out on the calculator that I have beside me, times 3 minus 16, we have a value of -4 actually. So in this case our profit is decreasing. So determine whether the profit is increasing or decreasing, we would say decreasing. So change in profit, change in time, it's a negative slope. In this case, something like this, it's negative, that means change in profit is decreasing. Alright, 1 year after the company was founded, the profit was $4,000. Find an expression for p of t when t is equal to 0. So 1 year after the company was founded, that would correspond to t is equal to 1, and we know the profit is equal to $4,000. Okay, so what they give us already is they give us, I'll write this out, part B, they give us this equation of dp over dt, which is the derivative. This is the equivalent of, let's say, p prime in some sense. the exact same, it's just different notation, minus 8t. But we don't want p prime, we just want an equation for p, or p of t. So remember, if we have, let's say, f prime of x, that's our derivative. If we want to reverse the process and just find f of x, we would take the antiderivative. So in this case, we have p prime, we want to find p itself, we want to find the original function that give us the derivative. In the formula booklet, we have this formula right here. If f prime of x is equal to x to the power of n, then our original function would have had an exponent greater than 1, but it also would have been divided by n plus 1, whatever that new exponent is. And you can think that that should make sense, because when we take the derivative of some function, we multiply out in front, and if we multiply and divide, these things should cancel out. So let's go ahead and work this out. So no variables in the denominator, we don't have like 1 over t in anything, so we should be able to just more straightforward use this formula right here. So let's begin with 3t, and 3t, previously it was 2, let's add 1 to that, and now it should be 3t over 3, and our new exponent is 3, this n plus 1 is now 3, so let's divide by that value as well. Minus 8t, if there's no exponent to t, it's just t to the power of 1. So if t to the power of 1, let's add 1, it's squared, and then let's divide by 2. Let's simplify. You can take these values and write them in your calculator and write 3 divided by 3, and 3 divided by 3 will just give you 1, so we have t cubed minus 8 over 2 is just going to give us 4t squared. And one thing that's, I think, kind of nice about taking the derivative, or sorry, finding the antiderivative like this, you can always reverse the process to find out. So there's 3 out in front would give us this 3t squared exactly, and this t squared right here would give us this negative 8t to the 1. So you can always test to see if you got it correct. Of course, when we're taking the derivative, it's not, we don't know whether there was some kind of constant c. Just plain numbers are reduced when we go back and we, let's say, take the derivative. So in this case, we don't know if there was some c, some constant, so we put this value c in here. What makes this a 4-mark question is that we want to find out the whole profit function, and for that we want to see what this value of c would be. We have an input, t is equal to 1, and we have an output of p is equal to 4,000. So given that we have 1, 2, 3 unknowns, if we know 2 out of 3, we should be able to substitute and solve. So p is equal to 4,000. T itself is just equal to 1. 1 cubed minus 4, 1 squared plus c. And now we've got an equation which we should be able to end solve. So let's go to the calculator and work that out. So menu, algebra, numerical solve. 4,000 equals to 1 cubed minus 4, 1 squared plus c, and we want to solve for c. So 4,003, rather peculiar. Let's go back to the document here. C is equal to 4,003. So let's go and write out the whole equation. We know that C is equal to 4,003. So profit as a function of time is equal to t cubed minus 4t squared plus 4,003. And that should be our profit. T cubed minus 4t plus c. I see. Okay, so I was wondering, I thought this was rather peculiar, but this is my mistake looking at this. So I wrote p is equal to 4,000 here. I wrote p is equal to 4,000. This is a danger of, I guess, close reading. This value seemed a little strange, that our value of C was so close to the original value of 4,000. But looking at it, where P is the company's profit in thousands. So in this case, this P is not equal to 4,000. P is equal to 4. It's $4,000. And to be honest, they actually even help us out in this sense by writing $4,000 instead of just 4,000. So P is the company's profit in thousands. So a lot of this will stand, but in terms of our inputs and outputs, let me just modify this real quick. We have P is equal to 4 when T is equal to 1. This is what we should be working with. So let me change this just slightly. Here P is equal to 4, so that's our 4,000. And now we can find C. So going back to the document, I'm just going to copy this and change. And then we have a value of 7. Okay, so let's go back to the document itself. C is equal to 7. And in this case, there it is. That's our final function. Okay, sometimes, to be honest, I apologize, but at the same time, potentially a decent kind of learning experience. If something seems rather peculiar, maybe it could potentially be an indication. Go back, see if there's anything. This 4,000, just in terms of the other coefficients in the 4,000, how close it was to the initial value or the given value of 4,000, 4,003, looked a little funny. So my mistake. Company's profit is measured in $4,000. P is equal to 4. Okay. Last question, 13-mark question here. A ball is dropped from a height of 1.8 meters and bounces on the ground. The maximum height reached by the ball after each bounce is 85% of the previous maximum height. Show that the maximum height reached by the ball after it has bounced for the 6th time is 68 centimeters to the nearest centimeter. Okay, so we have the ball. It's being dropped from an initial height of 1.8 meters, and then each time afterwards it only rises to 0.85 or 85% of its previous height. So if we were to write an equation for this, and let's say this is the bounces and this is the height, what could we do? So 0 bounces, it's at 1.8. After the first bounce, it goes up to 1.8 times 0.85. And I'm actually just going to work that out. 1.8 times 0.85 is 1.53. And then after the second bounce, again, we would multiply by 0.85. So in this case, we actually have a geometric sequence. When we have some starting value and we multiply by some constant term as we go through it, and we have a geometric sequence. So in this case, there's A. Show that the maximum height reached by the ball after it is bounced for the 6th time is 68 centimeters. Our geometric sequence formula is given by UN is equal to U1 times R n minus 1. U1 is the value of the first term, and R is the common ratio, what we multiply by to go from one term to the next. So conceptually, we can think of this, if we want to find the maximum height reached at its 6th bounce, we can ask ourselves, okay, well, how many times do we need to multiply by R, this 0.45, in order to get there? So here is 1, 2, and the distance should be, just 3rd bounce, 6th bounce, 5 times. So in this case, if we want to find the height from the 5th bounce, we know that U1 is going to be 1.53. So this one's a little tricky because our first bounce is right here. It's not actually equal to 1.8. This would be in some sense the drop height, so it's not yet bounced. The first bounce of u1 doesn't happen until we multiply 1.8 times 0.85. So this is our first bounce times, and then the common ratio of 0.85, and then times n. In this case, n is equal to 5, so let's just substitute 5 minus 1. 1.53 times 0.85 times 5 to the 1. So let's put this into the calculator. 1.53 times 0.85 raised to the power of 5 minus 1. 5 minus 1. Essentially 5 minus 1 is 4. It's not a bad idea to write that out just so you don't get mixed up for brackets or order operations or anything like that. Okay, so, or sorry, it's a 6 bounce, isn't it? So n minus 1 would be, I'm actually going to write it out this time, 6 minus 1. And there we have 0.678869. So going back to the document, we have 0.6789, or rounding to just to the nearest centimeter. Remember, this is in meters actually. This is in meters. So multiplying by 100, we have 67.89 centimeters, or 68 centimeters. Okay. Alright, so I think the trick in this one, or maybe the challenge, is this is the value of the first term. And the first term doesn't correspond to the drop height itself. It corresponds to the height reached after the first bounce. So drop height times that 0.85 or 85% to which it rises to. So that's our u1. And then r, we still know is our common ratio. And then n minus 1. N minus 1 is the n minus 1 is the number of times we're multiplying by to get 2, and since it's a sixth term, n is just going to be 6. I'm sorry, here I had written it as 5. So sixth term, 6 minus 1. Okay, part B. Find the number of times after the first bounce that the maximum height reached is greater than 10. So we've kind of done the hard work, and we've got an equation which is 1.53 times 0.85 n minus 1. Find the number of times after the first bounce that the maximum height reached is greater than 10 centimeters. So if we look at this, every single bounce it goes less and less and less and less and less and less. We want to find the number of times that this bounces such that the maximum height reached is greater than 10. So we know it's going to get less and less and less, but what is the number of bounces that we can possibly have where the bounce height is still just greater than 10? So maybe it just makes it over, and then the subsequent bounce would be, in this case, reduce that a little, just less than 10. So it doesn't quite measure up, not quite there. So we want to find what bounce is that, what number. Alright. Find the number of times after the first bounce that the maximum height reached is greater than 10. In this case, this value, this is un, which is just the value of the nth term. In this case, we want the value of the nth term to be equal to 10. So we have 10 is equal to 1.53 times 0.85 n minus 1. And in this case, we're looking for that value of n that's going to solve this. So we can just go ahead and n solve. Let's go ahead and do that. So menu, algebra. Solve 10 equals 1.53 times 0.85. Then we want to raise this to the power of n minus 1, and then we'll put a value of n. Okay. And for some reason, this says, I see. Okay, so sometimes this is just me being careless, to be honest. You can have a look and see what the problem is. This negative 10 is impossible. This 1.53 is measured in meters, where this was given to us in 10 centimeters. So negative value, obviously not really coherent. So we can either convert this into meters or convert this into centimeters. I think it's going to be easier to convert this 1.53 meters into centimeters, and 1.53 times 100 is just going to give us 153. And in this case, we have 17.7848 bounces. So going back to the document, in this case, n is equal to 17.78 bounces. So the number of times after the first bounce that the maximum height reached is greater than 10. At 17 bounces, we're still greater than 10. At 18 bounces, we would be less than 10 centimeters because each bounce we're decreasing. We don't really have 17.78 bounces. We only have whole number for our bounces. So in this case, the number of times after the first bounce that the maximum height reached is greater than 10. In this case, n would be equal to 17. After the 18th bounce, we would then be smaller. Or after the 17th, once we reach the 18th, we'd be smaller. Okay, let's go to part C, asking us to find the total vertical distance traveled by the ball from the point at which it's dropped until the fourth bounce. So what makes this one a little challenging, and I suppose we could suspect that it might be challenging, given that it's the final question on a paper 1, and it's also a 3-mark question here. The total vertical distance is going to be not just this initial drop height, but what makes this extra challenging is that we have the ball traveling upwards, but also the ball traveling, of course, downwards on its way back. So the total distance that this ball travels would be not only its, on its way up, but the total vertical distance is going up and then going down again. So it makes it a little more challenging and some extra kind of pieces involved. So we've got this geometric sequence here, and we've got a formula for it right here. So let's go ahead, and if we know, let's say, the value of the first term, and we know the value of r, we should be able to find the sum of the terms of a geometric sequence using our geometric sequence formula. So let's go into the formula booklet. Here it is already, I suppose. I'm just going to erase this and then mark it up once again, I suppose. Here we go. So Sn is the sum of n terms, so the number of terms of a geometric sequence. U1 is the value of the first term, r, our common ratio, and then n is, of course, the number of terms that we want to find the value of. So let's go back to the document and write this out. So Sn is equal to U1, value of the first term, times Rn minus 1 over r minus 1. We saw that there were actually two formulas. I'm just going to write out the other one right here. R to the n over 1 minus r. They're the exact same thing, except these values of 1 and r are switched around. And what that does is when r is less than 1, so for example in our case we have 0.85. 0.85 minus 1 is just going to put a negative value. And so these formulas are actually equivalent. They mean the same thing, and you can use either one as long as you're mindful of your brackets and so, and your negatives. Either will be okay. So it's just to avoid negatives if you wanted to work this out maybe by hand, I suppose, or in smaller parts. So let's go ahead and work this out, reading the question really carefully this time. Find the total vertical distance the ball is dropped until the fourth bounce. So in this case, this is U1, this is U2, and this is U3. So this is just 1.8 right here. This is the value of U1, the value of U2, and this is the value of U3. We don't want to include the fourth bounce. It's until the fourth bounce, which is dropped until the fourth bounce. Maybe some kind of ambiguity here, but the idea is we don't want n is equal to 4. We don't want to include this last height. We just want n is equal to 3. So let's go ahead and find the sum of the first 3 bounces. So U1, 1.53, common ratio of 0.85. In this case, n is equal to 3, minus 1 over 0.85 minus 1. Let's go ahead and put that into the calculator. So 1.53 times, I'm going to open up some brackets and then get a fraction here. 0.85 to the power of 3 minus 1. Then we have 0.85 minus 1. Okay. And there we go. Let's go back to the document. The value is 3.9359. Remember, this is all in meters so far. And so to 3 sig figs, I'm going to write this out as 3.94. Okay, 3.94 meters. And just looking back here, just to get a conceptual idea, this initial drop height was 1.8, and then the sum of the heights of each of these is going to be, actually, was it 3.94? But really, that's just the vertical height on the way up. So blue is equal to 3.94, and then on the way down, it's also another 3.94. So a lot of pieces to potentially, maybe kind of trip you up in some kind of way. And to be honest, I mean, it did for me the first time I read this. 1.8, sure, we have to only have one bounce here. It's the way up and the way down. Multiply by 2, sure, but this part until the fourth bounce. So we don't actually include this value of U4 in this instance. It's only up until this value, so we only want to take the first 3 bounces. So putting it all together, total value, that initial height of 1.8, that's the initial drop height, plus 2 times the sum of the next 3 bounces. I'm actually going to write out all of the digits just because we don't really want to put 3 sig figs until the question is over at the end. So 3.9359. And let's work that out. I'm going to put that on my calculator that I have beside me. 3.9359 multiply by 2 and then add 1.8. And this gives us 9.67 meters. And it doesn't ask for centimeters or meters, so we can just keep it like that. Okay, alright everyone. Not a bad exam. There's some questions that definitely required some more interpretation. The earthquake question, for example, this final question, where a close reading is potentially super important. I suppose all along, though, make sure to show process marks, maximize, and of course you'll be rewarded in that sense. Alright, otherwise, I hope it was helpful, and as always, of course, best of luck. Best of luck.